All right, when you think of chemical reactions, what do you think of? First thing to mind, ready, go? Motion, spoon, what else? Energy, fire, rusting, changes, acid, what? Bases, reactants, okay, redox. All right, so chem homework. All right, there we go. I heard chem homework. Hey, you got to do it, so that's the way it is. Now, the cool thing is, today we're going to be talking about chemical reactions and the part of chemical reactions which involves keeping track of them, called equations. Now, in chemical reactions, some of you may have seen these things before. Let me just make sure my working. There we go. The quote of the day is from Ralph Waldo Emerson. It is a superstition to insist on a special diet. All is made at last in the same chemical. Whether you honor a special diet or not, all you're eating are atoms. And the amazing thing about the food you eat is most of the food you eat is made of the same atoms. Even ice cream. However, the small differences that we see, the good thing about balancing chemical reactions and keeping track of them, is we can see the differences, the amazing differences in our world around us. Chemical reaction. A simple definition is a process in which one or more substances come together in a chemical reaction. So when a change happens and new substances form, it could be one or more forming or one or more coming together or vice versa. This is called a chemical reaction. It is abbreviated RXN in chemistry. Anytime you see RXN, it is not someone's name, it is a chemical reaction. On the ingredient side, it's called the reactants. So on the left side, chemists always put the ingredients, what's being added together on the left, and then what is being produced goes on the right. The arrow in between means to produce, or if you want to have really fun with words, it also means yields, which means to produce. In a chemical reaction, we may have something like our gasoline engines in our automobile that you may have drove to school on, or if you had the pleasure of walking, you may have seen these. You had octane, which is a component of gasoline, combining with oxygen. Those combine together in the automobile engine, and the products are carbon dioxide and water. Just two of the products of this combustion reaction. This would be called a complete reaction. So everything that you put in reacts to form the products on the right-hand side. Evidence for chemical reactions. One, a gas is produced. So if you see gases produced, there's evidence of a chemical reaction. A permanent color change is observed. So if it starts out blue and it ends up black, that could be evidence of a chemical reaction. An energy change occurs. Or a precipitate is formed. A precipitate is a solid product from a mixture of liquids. Now the word precipitate has a really cool history to it. When you think of the word precipitation, what comes to mind first? Rain. Now rain is unique because the air is a mixture. It's a homogeneous mixture. And there is water droplets, there is water, gaseous water in the air right now that's invisible that you cannot see. And when it forms a cloud, it is coming out of that solution of air, it is coming out and forming drops. Those drops, due to gravity, fall out of the air to the ground, and they're called rain. That precipitation process is true for rain, and for snow, and for hail, and for sleet, and for all sorts of other things that we don't know in Southern California. Precipitation is something going from a gas phase in weather to a liquid or solid phase and falling out of that solution. Now the air is a unique solution compared to gases. This precipitate in chemistry is commonly referring to a solid. That's solid. You got liquid, 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 solid. falls out of the solution. Now, we saw this on the first day with our lead iodide. Now, falls out of solution. What does that mean to fall out of solution? Does it like jump out? Does it like leave the solution? Does it go somewhere else? Let's check out what happened with the lead iodide. So here was our yellow liquid from the first day. You'll notice that there's still some yellow particles in the liquid. But on the bottom, you see a majority of the yellow solid. That's what's meant by precipitation. Now, this is a precipitate that formed in this reaction. The reaction is called a precipitation reaction because the precipitate formed. Pretty obvious. But that here is what we can see a precipitate as. So if you can remember rain, you can remember a solid falling out of solution. Just have to remember the phases are a little different. This is a video of the reaction we did on the first day. Two clear liquids being poured together, and that yellow stuff is lead iodide. That is a precipitate that forms. If they let this sit for a few days, precipitate due to gravity would be pulled down to the bottom because it is more dense than liquid water. Now, chemical equation uses chemical symbols to show what is happening. There are three ways of representing the reaction of H2 with O2 to produce H2O. First way is you got two hydrogen molecules connecting to one oxygen molecule, forming two water molecules. That's one way of representing this reaction. Here's a picture representing this reaction. Two of those, one of these, making two of these. Another way of showing this is two H2s plus one O2 makes two H2Os. Three ways of representing this same reaction. You could even think of a fourth way. Instead of saying you have two hydrogen molecules, you could increase the number to a factor of 6.02 times 10 to the 23rd, or 6.022 times 10 to the 23rd. And that would be 1 mole. So instead of having two hydrogen molecules, now you got 2 moles of hydrogen molecules, plus 1 mole of oxygen molecules makes 2 moles of water molecules. You can just add that in there. It still shows the same relationship. Now, chemical equations. The direction of the equation arrow can vary. So, Mg plus O2, magnesium plus oxygen, forms magnesium oxide. These two are the reactants on the left. This one is the product on the right. The arrow is reversed. This here would be the products, and that would be the reactants. So the arrow definitely does have an influence of which side is the products or reactants. This here is another way of showing Mg plus O2 forms MgO, and MgO breaks up to form O2 and Mg. So it's going forward, and it's also going in reverse, although how you define forward depends on your arrow. Yes, sir? These equations, I don't think we've talked about that yet, no. So they are just showing the relationship. Looks like it's not. Now, this state where you have a double arrow is called equilibrium. And that's where the forward rate of reaction equals the reverse rate of reaction. Now, when you have these chemical equations, the state of each substance may be denoted. So Mg here is a solid, oxygen is a gas, MgO is a solid. So the letters for showing this are gas is G, S is what? Solid, L, usually it's a cursive L if you're writing it. A little harder to find cursive L's. An L is a liquid, solid, and then there's one more state in which the substance is dissolved in water, and that's called aqueous. So that means it's dissolved in water. That's usually the only new state that people hear in this particular slide. The rest people have experienced before in one way or another. Now, the easy way to remember aqueous is aqueous comes from the root aqua, and my favorite superhero is Aquaman. And so if you think of one person that would like to be Aquaman, it's who? You, that's right. And the substance that is dissolved in water is called the solute. And if I was Aquaman and I dove into water, I would dive in, and that makes what's called the solvent, is what's called water. So Aquaman's got the answers for dissolved in water. If you remember that you want to be Aquaman, you meaning Mr. Crystal. If you want to say you want to be Aquaman or someone else, that's up to you how you decide that. But I love Aquaman. All right. That's how I remember that. Now, the cool thing is law of conservation of mass. This is one of the coolest things about chemistry, and it's the simplest thing about chemistry. Basically, it means that matter can neither be created nor destroyed. Okay? I can't just wish to be rich and have matter appear in my hand that says I'm rich. Okay? The good thing about monetary money these days is most of it is electronic anyways. So just learn about that and you're fine. But you cannot just create, you can't get something from nothing, and you can't create something new out of nothing. Things don't just appear out of nowhere. Law of conservation of mass. Now, in any chemical reaction, the total mass of reactants must equal the total mass of the products. So before must equal after. Reactants is before the reaction, products is after the reaction. The reactants turn into the products. So you have to make sure they're equal on each side. In 1789, it's first demonstrated experimentally by the Lavoisiers. Antoine and Mary Anne, called the Lavoisiers, although you can see they don't necessarily have the same last name. During a chemical reaction, atoms do not change, they merely rearrange. So the atoms rearrange position, but they do not change. Now, Antoine Lavoisier being the first to show experimentally this balancing of matter is called the father of chemistry. And you could argue for the mother of chemistry, but they don't usually talk about her. So in the experiments that were done in the laboratory, we're dealing with ratios and the amount of substance. And they were able to contain substances and see how much in a chemical reaction would be produced and whether that amount actually changed. When we read a chemical equation, this here means we have 2 atoms of Mg plus 1 molecule of O2 makes 2 formula units of MgO. So this is an atom. This is a formula for a molecule. This is a formula unit for an ionic compound. So that's how you would read this equation here. You could also read it, instead of doing it in terms of the atoms, molecule, and formula units, the moles makes it a little bit easier. You don't have to think about whether that's an atom or not. You just say 2 moles of magnesium plus 1 mole of oxygen makes 2 moles of magnesium oxide. The next way of showing the relationship in a chemical equation is here. 2 moles of magnesium is equal to 48.6 grams of magnesium. 1 mole of oxygen is 32 grams of oxygen. This makes 80.6 grams of MgO. If you add these 2 together, this plus this will equal that for the mass. So the mass before and the mass after have to be equal. However, if you have 2 grams of Mg and you add 1 gram of O2, that does not make 2 grams of MgO. But if you look up here, wait a minute, there's a 2 there. There's an invisible 1 there. And there's a 2 there. So that seems to be a problem. We've got 2 of these plus 1 of these, and you say that equals 2? 2 plus 1 equals 2. In math class, would you have passed if you said that? Yeah. If you could prove it. If you could prove it, yeah. If you could prove it in geometry, you're fine. But 2 plus 1 equaling 2. There's a little bit of a challenge here. So what you're seeing here is the mass does equal. This plus that does equal that. However, the moles do not equal. The moles do not necessarily equal. Now, one way of showing this, which isn't the best in the world, is by using a whiteboard pen. So here we have a whiteboard pen, and we need 2 magnesiums and 1 oxygen. So we need 2 Mgs and 1 O. So we'll make it easy. Here we go. 1 Mg, 1 Mg, and 1 O. So here we've got how many total pens? Got 3 of them. Got 2 here and 1 here. Now what happens is they react together to form MgO. 2 Mgs, 1 O. Oh, I need an O2, yeah. Where's my O2? Oh, yeah. So here's my O2, pardon me, I said it was an O, it's an O2. So our Mg reacts with one of the O's, the O breaks apart, and the other O reacts with our original Mg, and these here are 2 identical MgOs. They don't look identical. It works a lot better with layers. Okay? Alright? So the challenge is you make 2 things out of 3 things. So that is a very common thing. Oftentimes you can show this with other compounds. If you've got 1 of these, you got 2 pieces to it. You always got a top and a pen. So that's one of the unique things about balancing equations and about moles and grams. Grams are going to be equal. Left side equals the right side all the time. Moles are not necessarily going to be equal. Now, equations must obey the law of conservation of mass. Mg plus O making MgO. Uh-oh, that doesn't obey, because Mg is 1 Mg here, 1 Mg. 1 O here, but there's how many O's here? 2. That is not obeying the law of conservation of mass. So this is not what's called a balanced equation. So when we keep track of them, 1 Mg and 2 O's on that side, 1 Mg and 1 O, in order to make sure that they are balanced or obey the law of conservation of mass, you write whole number coefficients. So the coefficients are added to balance the equation. So those are the numbers that go in front of the formulas. So if you put a 2 in front of the MgO here, this makes the O happy. There's 2 O's. But the Mg, there's 2 Mg's here, but there's only 1 on the left side. So you would have to put 2 in front of that Mg as well. Now the Mg's are happy. There's 2 on the left and 2 on the right. Here there's 2 O's and 2 O's. The number of atoms on the left and type of atoms are equal to the number of atoms and type of atoms on the right side. So the first step in writing and balancing chemical equation is write the correct formula or formulas for the reactants on the left side and the correct formula or formulas for the products on the right side of the equation. So before you even balance an equation, you must write the correct formulas. So one of the reasons why we went through formulas and naming before we even looked at balancing equations. It's first. It's first. If you don't do the formulas, well, it's really sad, but you get the, don't do the formulas, you get the F, how do you spell formulas? You get the F? No. If you don't write the correct formulas, you can never spell formulas begins with F, you get a F. I don't know the rest of it, but I don't want that to happen to you. So I would like you to be successful. I got problem spelling, so let's not get into that. All right, number 2. Next thing you do is here we've got correct formulas. So here you got words. So here you got words. Ethane reacts with oxygen to form carbon dioxide and water. Okay, now we're trying to come up with formulas of these. You may know some of these formulas, other ones you may not know yet. Okay. Okay. Anyone know the formula of water? H2O. Now, what about carbon dioxide? CO2. Very good. And there's no mono in front of the carbon there. Oxygen. O what? O2. Why is it? Diatomic. 7 is 7. All right, so we know all those. The one we may not know is the ethane, which is okay. We haven't talked at all about its formula and where that comes from. So, once you know all the language of chemistry, you read it, then you write the formulas. So, ethane happens to be C2H6. There's our oxygen, O2, carbon dioxide, and water. So we've writ the formulas. However, you'll notice that that doesn't mean that it's going to be balanced. Just write the formulas, you're like, okay, good job, congratulations. But it's not going to be balanced. It won't follow the law. So then you change the numbers in front of the formulas, coefficients, to make the number of atoms on each the same. Do not change the little numbers, the subscripts. Okay? Now, I'm not incredibly tall, so I usually say don't screw with the little guy. All right? Little guys usually have a little attitude. Right? You mess with them and you get all this stuff rained down on you. Now, it's not all little guys. I know big guys are the same way. But don't mess with the little numbers. The little numbers are the formula. You can't change the formula halfway through. You're like, oh, I don't want O2 anymore. I'm just going to have O. I just want one of those. No, you can't do that. You can't change it in a formula. So just be aware of that. That's a trick that I see a lot of imaginative scientists try to do. Change the numbers halfway through. So you don't change it. You can only change the big numbers, the coefficients. So you cannot put C4H12 just because you feel like it. You have to put 2 C2H6 to make it balanced. Okay? So this is 2 moles of ethane. This here is not ethane at all. In step 3, start by balancing those elements that appear only one reactant in one product. So the simplest ones are the ones that appear only in one thing on each side. So in this case, what appears in only one thing on each side? C does. And so does H. So C or H would be the first thing to start with. So, start with C or H, but not O, because O is in almost everything. Not everything, almost everything. So you got 2 carbons on the left, 1 carbon on the right. Multiply the CO2 by 2. That changes it. So now we have 6 hydrogens on the left, 2 hydrogens on the right. What do we have to multiply the right side by, the H2O by? 3. So 2 times 3 equaling 6. Multiply H2O by 3, just like that. So now the C's and the H's are happy. They are equal on each side, the left side and the right side. The last thing we have to do is check, is the O equal on each side? So I really quickly count up here. We got 2 O's on this side. We've got 2 times 2 is 4. 3 times 1 is 3. 4 plus 3, that looks like 7. Let's see what it looks like here. This is step 4. You balance those elements that appear in 2 or more reactants or products, which in this case happen to be the oxygen. There's 2 on the left, 4 oxygen in CO2, and 3 oxygen in H2O. 3 H2Os. So you've got a little thing here where you've got 2 here and 7 here. So 2 times what equals 7? 3.5. So there's 7 on the right, only 2 on the left. How do we determine how many we want to have? You take the O2 by 7 halves. If you multiply 2 by 7 halves, you want 7, and you have 2. You don't even have to do the 3.5 calculation. You can just write down what you want and what you have. Makes it easy. So you put the 7 halves here. Okay. Now once you have the 7 halves, the oxygens are equal, the H's are equal, the C's are equal, everybody's happy. However, we have to remove the fraction. Now, this is the easiest part. If you've taken math, all you do is multiply both sides by 2 to get rid of that denominator. So the entire equation is multiplied by 2. 2 times 1, 2, 7, 4, 6. Okay? So you usually wait for that till the last. This is one of the reasons why we did oxygen last. It is often very helpful to use this halvesy method. Sometimes it doesn't turn out to be halvesy. Sometimes it turns out to be like the 30s or something crazy like that. But usually halvesies tend to happen in these type of reactions. So those are the steps, 4 steps for balancing chemical equations. The 5th step, once you have that done, check to make sure you have the same number on each side. If you don't have the same number, you may have just miscounted at some point, okay? Or made a mistake, and then your equation will be wrong forever. So, quickly double check to make sure you've got the right amounts. This is called inventory management. Here you've got 4 C's, 12 H's on each side, and 14 O's on each side. Double check. Here's our reactants, here's our products, everything checks out. Okay, this is a way of inspecting the equation. So, what I would like you to do is there are 4 equations. Using the techniques we just learned, please balance these 4 equations on your paper. If you have notes, please try to put them away and do this from memory as much as possible. You can go back to the notes, obviously, as needed, but try to do it without looking. So on these 4 here, the coefficients that you should have gotten for these 4 are up here in purple. For this one here, number 3, the trick that I usually see is when you have a single O in the first substance with O2, CO2, and H2O, this is a pretty common type of reaction. When there's a single O here, this here, again, you have to have the same even number of oxygens on each side or odd number of oxygens. Usually it's easier to make it an even number of oxygen on each side and then reduce it if necessary. So in this case, you can't reduce it, but that's why it's 2764. In this one, the trick on this one is keeping the polyatomic or the oxy ions together. S2O3 is an ion. Na is an ion. Fe is an ion, and NO3 is an ion. So you group them as entire things when you're keeping track of them. Here you've got an S2O3, 1 of them. Here you've got 3 of them. So you put a 3 in front. Okay? Then you got 3 times 2 is 6 of them. So you put a 6 in front. Then you got 6 NO3s. Here you've got only 3s. You multiply it by 2. That makes 2 Fe's. There's 2 Fe's. You're done. It makes it a little bit easier than counting each individual atom when you have ionic compounds. So when you see ionic compounds, you can group them together. Now, when we translate equations from English, okay, the plus sign means and, with, mixed, or dissolved. The arrow means produce, decompose, combust, burned, electrolyzed, or formed. S usually means precipitate, suspension, turnings, pellet, or ribbon. They're all different ways of describing solid materials, especially metals, that is. But precipitates and suspensions, and then turning, pellet, and ribbon are all different ways of getting elemental metals. Liquid sometimes is described as molten, especially with a material that you wouldn't think of as being a liquid. It would be at a high temperature. Aqueous is usually solution or acid. It's a homogeneous solution. Acids are one of those type of aqueous solutions. So if we take these equations, we now want to take the names and using our ions, and our knowledge of nomenclature, we're going to take these names and write equations. The first step is to write correct formulas. Then, after you write the correct formulas, you're going to balance the equations. So these 4 here, I'd like you to try to do at least 2 of these 4, if not all 4 of them right now. For these here, the one thing you got to pay attention to is the formulas, and then putting them together. So this here is lead 2 nitrate, potassium chromate, lead chromate, and potassium nitrate. And then you only need a 2 in front of this to balance the entire equation. Again, ionic compounds, you can group them together. The zinc metal reacting with hydrochloric acid produces zinc chloride and hydrogen gas. Remember, hydrogen gas is diatomic when you balance that out. Third one and fourth one, which we may not have gotten a chance to do.
Whoa.
What? Yeah. So these are the answers for 3 and 4. If you did get a chance to get that far. Tomorrow we have our ion quiz number 1. Aluminum to cadmium and ethanoate to bicarbonate. One thing you'll want to print out, which I don't know if we have the lab manuals yet, is the Chalk Lab balancing equations worksheet, which is the back of the blue sheet. That is the homework for tonight. This here is a sample ion quiz for you. Alright, so please raise your hand, give me an answer to one of these, and you'll be the first ones that can go. Yes, sir? Barium. Alright, that's what you do after they die? Yeah. What? NH41 plus is this one. Yeah. Al3 plus is which one? This one? Alright, cool. Other ones you know, yeah? Bismuth. Parentheses. 3. Alright, yes, sir.
4 is BrO3 1
Bro, yeah, yeah. Alright, yeah. Arsenide. Alright, yeah. Alright, ethanoate, also known as acetate, and bicarbonate. CO3 with what? HCO3. Alright, have a fabulous evening. We'll see you tomorrow.